subject that apparently I know how to talk about, and that's the planet Mars. We heard a very stirring video just now, and I want to talk about where we are today in our Mars exploration program and talk about why we're going to Mars today, what we're doing there, and where we're headed. Do I have control over the charts? Yes. So I want to really take a step back and not just talk about the science, but talk about why we're doing Mars exploration and start with the public's fascination with Mars as a place to explore. I think we're all familiar with some of the different aspects of this. The face on Mars off on the left. Many of you are familiar with that thing in the bottom middle. If you are, I don't need to tell you what it is. If you're not, I can't explain it. But we've seen in the upper left videos and music related to Mars. In the lower left, a group called 30 Seconds to Mars that happened for this picture to be touring in Estonia, of all places, and seeing Mars in Estonia is an exciting opportunity. We're all familiar with War of the Worlds, packing for Mars. The real driver behind Mars exploration, though, is, and the reason the public is excited about it, is the possibility that there could be life on Mars. Mars meets all of the requirements we would put on an environment to be able to support life today, or to have supported an origin of life 3 or 4 billion years ago: liquid water, all the elements that you need to construct living things, and a source of energy that can drive metabolism. We see here the Mars meteorite, one of the Mars meteorites, Allen Hills 84001 on the left, and a microphotograph on the right that provides some of the input that the public has seen for trying to understand it. It really begs the question of did Mars ever have life? If it does have life, is it related to life on Earth, or does it represent an independent origin? How does life, if there is any, interact with its planetary environment? And given that it's the environment that supports life, how has the habitability of Mars by microbes changed over time? What is it that turned Mars from apparently an environment 4 billion years ago capable of supporting life to one today that really doesn't look like it's able to? We have really a fleet of spacecraft exploring Mars right now. The ones on the far left are operational. There are 5 orbiters that are looking at Mars right now from 3 different space agencies, and 2 rovers on the surface. And to me, that is just an amazing opportunity to learn about Mars. This is just the tip of the iceberg. We've had a lot of missions to Mars over the years. I don't know the numbers internationally, but the U.S. has had 16 successful missions, its share of unsuccessful missions as well. But that's a tremendous amount of knowledge about the planet. And I want to talk a little bit about some of the findings and that relate to Mars habitability and some of what's going on today. These are images from Mars Reconnaissance Orbiter. It's been exploring Mars through high-resolution imaging and through compositional imaging. And we see here on the top an image that has compositional information superimposed on it. Up here is, you can see right where the dot is, pointing at the Curiosity rover, and next to it, Gale Crater, where we might be exploring with a subsequent rover. We see a lot of evidence here compositionally for liquid water having been present. We see minerals that are present, that are produced only in the presence of liquid water. So we know that there's been liquid water flowing at the surface. We see evidence of it that's actually very widespread over the planet, and hopefully that's telling us something profound about the nature of the Mars environment. When we look from the surface with this panorama from MSL, we see what looks like just a rock-strewn surface. It could be a desert anywhere on Earth or anywhere on Mars, and it looks relatively uninteresting. But when you look close up, you see features, again, that tell us about the presence of water. The layering seen in these rocks is very typical of deposits that are laid down in standing water. And from MSL, from the from the Opportunity rover, from the Spirit rover, we see widespread evidence for liquid water having been on the surface. The presence of liquid water really is the harshest, most difficult requirement to be able to support life. So what we're doing with these rovers is exploring the habitability of Mars. And we think that the liquid water that is there is telling us about the environment 3 to 4 billion years ago on the planet. And I want to now go a different direction and ask, where did the water go? Where did the CO2 go that must have produced an environment capable of supporting liquid water? That is, you couldn't put liquid water and have it standing on the surface today on Mars. It's too cold, it's too dry, it would either freeze or evaporate, or freeze, then evaporate, take your pick. And conditions must have been different on early Mars. There's the abundant evidence for liquid water here seen in what look like river-carved channels. In one of the Mars meteorites, deposits of minerals that must have been produced by liquid water flowing through the rock. And where did that water go? Where did the CO2 go? What we're doing with the MAVEN mission, and I'm going to talk about MAVEN now, is exploring whether those gases could have been lost out the top of the atmosphere to space. We see evidence from the European Mars Express mission for gas that is in the process of being lost. The colors represent ions that are being stripped away from the atmosphere. So we know that that process has occurred. What we don't know is how important that has been relative to other processes. People have been looking for the carbonate deposits that the CO2 would have formed in the crust. They've been looking for where the water resides today. If it's lost to space, it ain't on the planet today. The MAVEN mission, MAVEN stands for Mars Atmosphere and Volatile Evolution Mission. I'm the principal investigator on that. We launched, launch now is ancient history. We've been in orbit since September of last year, and we're about 4 months into our primary science mission now. And I want to talk a little bit about what we're trying to do. We're exploring the role of the interaction of the sun with the upper atmosphere. And we're trying to measure the solar energetic inputs in the form of solar energetic particles, the solar wind, and extreme ultraviolet photons that can drive processes in the upper atmosphere. This cartoon shows a lot of the different processes that we might expect to be operating at the top of the atmosphere that could lead to loss to space, but we haven't really observed much of these, and we're going to try to understand what they look like, what the processes look like. Oh, here we go. We launched in November of 2013. Like I said, ancient history. It took 10 months to get there, and we went into orbit on September 21st. This picture, by the way, is not to scale. Thank you for that pity laugh, at least. The spacecraft is shown in this artist rendition in the bottom left. It was designed specifically for this mission to have the instruments that need to point at the sun, pointing at the sun, those that need to point at the planet, pointing at the planet, and those that don't care where they point, sitting somewhere on the spacecraft. The high gain antenna in the middle give you a sense of scale is 2 meters across. We're in the middle of our science mission. This is the orbit now shown to scale. It's elliptical. At the highest point, it's about 6,200 kilometers above the surface. At the lowest point, it's 150, and we occasionally lower it to 125. What that means is every orbit we're passing through the entire column of upper atmosphere and sampling it, and we're able to get a sense of what's really going on the planet. I want to show you some of the early results. The first thing we had to do was deal with comet Siding Spring, which arrived at Mars 4 weeks after we did, while we're still in our commissioning phase. It's a rather unassuming comet that stands out by virtue of the fact that in October it passed about 140,000 kilometers away from Mars, which is really, really close. And I'll tell you, we were worried that dust and debris from the comet would kill our spacecraft. Early on, we gave some thought to, is it even safe to launch? We did, we survived, so no problem. we took an image in the ultraviolet about 2 days before closest approach. This is what a comet looks like in the ultraviolet. You're seeing most of the stuff that is surrounding the comet. What you see in the visible images is the dust. We're seeing the gas here, which is more abundant. What's most important is if you look at this image, the distance, the missed distance from Mars is out about here, and the gas and dust is bigger than that. So we actually were worried that we would get hit by it. We adjusted where we were in the orbit to be shielded by the planet during the time of peak risk. We turned off the high voltage to make sure there wasn't going to be a problem. There were no problems, fortunately. And we turned on as soon as possible following that close approach because we wanted to see what the effects were on the Mars atmosphere. And lo and behold, we discovered some things. The first is we saw ultraviolet emission from the atmosphere indicative of metal ions from the dust. You can see the blue is before, the red is after, and look at that big peak. It's the biggest feature we've ever seen in the ultraviolet on Mars, and it's due to, I forget whether this one is iron or magnesium ions, but these three features are due to both of them. The dust would have hit the Mars upper atmosphere at 56 kilometers per second, vaporize, ionize, and produce a meteoritic debris layer at around 100 kilometers, and that's what we're detecting here in the ultraviolet. We also detected it in situ with our mass spectrometer, direct detection of magnesium, and here showing titanium ions. We detected 11 different metals because they're the ones you can detect easily, and they wouldn't be there otherwise. These disappeared after a few days. We expect that there would be a long-lived layer from debris coming in all the time, but we were surprised to see such compelling evidence for this layer. But we're really there to look at the escape, and on orbit 1 around Mars, we again turned on very quickly to see from that high initial orbit what we could see, and we saw these upper atmospheric layers of carbon, oxygen, and a very extended layer of hydrogen. What we're seeing is the individual atoms that comprise CO2 and water on their way to escaping. So we're looking at the start of the chain of escape, and the goal of MAVEN is to see that chain throughout the whole mission. And what I want to do is show you one piece of evidence that we've seen that tells us about that. This is from one of the instruments that measures energetic ions, and its mass up on this axis and energy on this axis. So you can see this big peak due to O2+, a peak due to O+, helium, H2+, H+. This is measured at an altitude of 250 kilometers, 300 kilometers, 400, and 500. This stuff is being energized and is getting more energetic. And this stuff is on its way to escaping. It's gone. So we're seeing the processes in action, not inaction, in action, that are leading to escape. Our goal now with MAVEN, these were measurements made in November, December. Our goal now is to understand the processes that drive this so we can understand how they've operated over the last 4 billion years of history and how much water, how much CO2 has escaped. Coming up next, in terms of this issue of habitability, is the Mars 2020 rover. This is a schematic of it showing the science instruments. From my perspective, the important thing is this is continuing the exploration of habitability and is going to be the first step, we hope, in sample return by collecting samples that will be returned to Earth. This is the same picture I showed earlier, but now showing the themes of the Mars exploration program, starting off with follow the water. Where did the water go? Where is there water? And MAVEN fits into that follow the water theme because we're following it as it's escaping to space. We're not following it just looking for it. We're looking for where it's going. We've been exploring the habitability of Mars. In particular, the Curiosity rover has been looking at habitability in a lot of detail at a few sites, and 2020 will continue that. And all of this really takes us along the path of preparing for human explorers, because these are questions that can easily, or at least readily, not easy, readily be addressed with humans in the loop. And I would hate to think that I live in a world where we're not going to be on a path to explore Mars with people, and we're working toward that with the robotic program. So I'll end there. Thank you.
Okay, thanks. Well, that was great to lead into what I'm going to talk to you about. And I wanted to thank Harley especially for asking me to come here and talk to you about the exciting subject of 2 workshops, and to put me also in the position of being between you and lunch. So with that challenge, I'm going to tell you that actually I'm excited. I'm very excited. I was really energized by Bob Rogers' talk yesterday, and I wanted to start off by telling you, referring back to Bob's talk, what this is really all about is we're trying to get out of that circular firing squad that he described. And I'm going to tell you a few exciting things that have happened on that front already. The other thing that's going on right now, I think, and I wanted to refer back to Charlie's comments yesterday, I think we really are, and here's the tie-in to the conference, we are on the cusp of breaking the 20-year barrier. Okay, you heard it here first, but I really believe it. He said it yesterday, and I believe it. I think we're there. So let's go through and see what we're doing. So the first chart here is something not from the 2 Affording Mars workshops, but from the mind of Joe Cassady. One of the things that I do in my spare time, and I was laughing at Mary Lynn's comment about needing to get a life, I sit around and read old Mars plans, okay? And they, believe me, there's a lot of them. I have a whole bookshelf full of them. So I said to myself, because I do have to dust them every so often, and they seem to be gathering a lot of dust. So why is that? Why is it that Mars plans have never been really, taken and implemented? And I'm talking humans to Mars now. And so the number one reason, if we were doing the Dave Letterman top 10 list, the number one reason is usually sticker shock. And that's because when we look at all the things we need to take out there, after all, it's like the ultimate backpacking trip, right? We've got to take everything with us. It adds up to needing to lift a lot of stuff off of the surface of the planet, and that adds up to a lot of money, a lot of launches, a lot of cost. And that sticker shock usually gets people like William Proxmire and others who've come after him excited, and they say things like, not one penny, for that folly. The second one is the Earth-dependent aspect. We try to look at things the way we've done them before. And what we have right now, as you've heard before, even with ISS, is very Earth-dependent. And so that's the second part. We've got to break that. We've got to break that to go to Mars. We've got to be able to get out of that dependency of needing Earth to help us and figure out how we can go out and, to a certain degree, live off the land, but also make our own decisions. I mean, we run into that right now with the rovers, the robots that are there. We have to go slower because we want to be careful, and they have a lot of autonomy built into them, but we still are careful. The third thing is we've always said, if we wait 10 more years, we're going to have this newfangled propulsion system, and it'll be better, and then we can get there faster, and that'll make it a lot easier. Propulsion just being my particular field, but you could say that for whatever field, Eclipse, you name it. It's one of those things that have bedeviled us over the years. The last thing, or the couple of last things, one is an assumption of reduced launch cost. We've always said, and this kind of ties into the one before, as soon as we get down to $100 a pound to orbit, it'll be duck soup. We can do it, no problem. And then the last one is really the key that we've been looking at in these workshops, and that is it's a multi-decadal program. You heard in the Boeing video, Mike Raftery say that. So how do we do that? How do we sustain a multi-decadal program and keep the budgets there to do it? Okay, so now we get into the workshops. These are exciting workshops. So why did we think we needed these Affording Mars workshops? Well, the big thing there was, and this refers back to Bob again, I really loved his talk. we identified the villain. Okay, we figured out who the villain was. The villain was this boogeyman of the $1 trillion Mars mission. You know, everybody gets a whiff of some previous study or something and they say, yeah, you know, it takes $1 trillion or $500 billion, you name it, whatever the figure is, to do a human Mars mission, and we're just not ready to put that kind of investment out there. So I want to tell you about, and you saw in the Boeing video, one example, but there's a number. At Aerojet, we did one. Other companies have done them. Other entities out there are beginning to look at this. New kinds of architectures where we can start to attack some of those things on the previous chart and bring that dollar figure down and figure out how to do it in a sustainable fashion. The second thing was we figured out we really need to go out and reach out beyond. There was always this little clique of us that wanted to put humans on Mars, and we'd get together and we'd talk off on the side. But what we figured out was you really need to broaden that out. We needed a bigger tent. We needed to bring in the scientists. We needed to bring in the folks doing the robotic missions, as well as international partners, as well as folks who want to go out and make money in space, and get us all together and start talking. Because, you know, it seems like when you look at it on the surface, we've got a lot of differences, but really what we found through these workshops is we also, while we have some differences about approaches and things like that, we have a lot more in common. So these are the folks that have come to the 2 Affording Mars workshops. There was one put on right here in town at George Washington University in 2013, and then just more recently in October of last year out at Caltech. About 60 folks each time from a variety of institutions, academia, industry, and government, 20 or so institutions in each case. And if you're interested in learning about what came out of them, there are actually reports that are published at the website that are shown there on the bottom of the chart. It's basically exploremars.org is the easy way to remember it. So I'm going to just really quickly, because I am between you and lunch, so I don't want to hold you up, I'm going to real quickly run through what came out of those 2 workshops. What did we agree on? What are these things that we found in common? So first stop on architectures, and this goes back to the video you saw with Mike there as well. We've come up with what we see, although we don't agree on everything, we see a very, very, very strong agreement that something like a split mission concept, and split mission just means don't take the crew and the cargo in the same thing. Split them apart, and the reason for that is, getting back to that thing of needing all that stuff to come up off of Earth, a lot of that ends up being propellant. And there's a whole lot of equipment. About 85% of what we need to get out to Mars is just equipment, it's supplies, it's underwear, all those kinds of mundane things. It doesn't matter if they go quickly or not. And we've got better forms of efficient in-space propulsion that can take those out there. Not fast, not as fast as we'd like it to be, but it also doesn't require any new physics, and it's here today. We're using it on commercial satellites today, and that's solar electric. You heard some of that referred to in the talks by Steve Jerzik and the other AAs yesterday. So that's going to be our way to get the cargo out there. And if you take all that out on the slow boat and pre-position it out there, it turns out it's not so bad to use even conventional cryopropulsion to get the humans out there, and you can do it in about the 7 to 9 months that people talk about. And if we can improve on that, if we can get a little better propulsion as we get closer to the 2030s, then that's even better from the standpoint of the human physiology, the radiation effects, and the microgravity. The other thing is we agree that we need these elements, and that was something you heard in the Boeing video as well. There's Mike Raftery's comment about 6 elements is right on. And the really cool thing is already we're working on the big rocket. We've got the SLS underway. We've flown Orion. We did the EFT-1 flight and demonstrated a big percentage of the required entry velocity on the heat shield. Just a stunning, stunning success. Yesterday out in Utah, we fired one of these big SLS solid rocket boosters. For Aerojet Rocketdyne, we're working with NASA right now on the RS-25 engines. We're going to have a test down at Stennis. So real stuff's coming together, real hardware on many of the pieces of this. What else do we need? We need this in-space transportation. This is our cargo vehicle here, using solar electric. We need better EDL technologies. And again, you heard folks yesterday, Steve Jerzyk and others, refer to the work that STMD is doing right now to pioneer that. So these are the basic elements that are starting to come together, and that's why I say I think we're well on our way to maybe breaking through that 20-year barrier. Another priority that we think came out of our conference that we think is very important is the idea that we need to go out and do some proving ground missions. We need a destination that will allow us to check out all the systems, and it's got to be someplace. I mean, the ISS is great, and we're getting a lot of good data out of ISS, but it's not outside the Van Allen belt, so it's not getting the galactic cosmic radiation environment that the astronauts would see on a long trip to Mars. So what we came up with was sort of what we call the bridge between ISS, and that's somewhat Earth reliant, and what we're going to need, the Earth independent kinds of vehicles to go to Mars. And so this is just a couple of concepts here, one by Boeing, one by Lockheed Martin, and all of these end up being something that you would do in cislunar space, which makes it very nice because it could be a platform to use for other types of exploration as well. But the idea is these would be progressively more ambitious missions. We'd use these as the place to facilitate doing that, and we can put all the systems, the ECLS, all the things that need to work on the way to Mars on board those, have crews go visit for progressively longer periods of time, and kind of do our shakedown cruise. The second one is some kind of a robotic precursor mission to do an EDL demo of something bigger than Curiosity. We're going to do Mars 2020 again, which is about 1 metric ton. We're thinking something that gets up maybe between 5 and 10 metric tons at least. We're going to need to put down at least 10 metric tons, if not 20, for human habs. So this is a very important thing, and it could be a Mars sample return mission. That's something else that's been discussed a lot, I know, and as one of the priority missions. So we're thinking again about how could we combine something that's important to science as a precursor mission, and also demonstrate technologies that are important for exploration. And one of the other things that mission could do, as Moxie's going to do on 2020, is do more ISRU demonstrations, because ISRU, in situ resource utilization, is going to be a very, very critical technology to close the loop and make this thing sustainable. And then a final consensus recommendation that I'll spend a little bit of time on, and then I'm going to go quickly through just several, was we really did see the value of having the scientists and the engineers and the architects all come together in these meetings. We weren't quite sure when we did the first one how it was going to work. Some of us were a little worried about those crazy scientists, but it turned out that we got such good interaction. We even had the planetary protection folks there, and some spirited debates, pretty good back and forth. But what we came away with is something that I think is a much stronger, it's going to be something that's defensible. It's going to be something that lots of us can get behind, and that's what's important in order for it to be sustainable. So just a few, as I said, I'll touch on these real briefly. And a couple of these may be a little controversial based on what I saw in the previous talks. One, and I think this is very important, we think that Mary Lynn referred to the flags and footprints missions. There's no way we're going to put all this effort, build up this infrastructure, spend this 20 years and a still substantial amount of money, even though it's not going to be $1 trillion, and just go put boots on the surface and put a couple of flags down for the partners that are there with us. We're going to want to go and stay. Whatever we do, we're building up a pathway. We're building up a thing that people can go and follow and eventually settle. But we think it should be based on something like the Antarctic outpost initially. So the elements that go on the first mission will contribute to a second mission and another mission, and I think it needs to be something like that that'll build on itself. And that can include the ISRU and other things that we could do. The second point there, we really did feel that a robotic sample return mission could be a very important precursor for the reasons I mentioned before, as well as something that would allow us to go through and pathfind how to do the forward and backward contamination protection before we land humans on Mars. the third point there, a lot of people talk about going to the Martian moons. It's a lot easier. We don't have to do a lander. On the other hand, we keep the astronauts in a microgravity environment for a lot longer. You're not getting much gravity. I saw that one slide yesterday of an astronaut standing on Phobos, I think it was, and that would be tough to do unless you had some pretty good golf shoes on to anchor yourself down. But at any rate, it could be useful, it could be interesting, maybe a really good place to do ISRU and make some rocket fuel to get ourselves back, but we didn't see it as enough. We thought the ultimate horizon goal has to be to put people on the surface. So only useful as a risk reducer or as a precursor, but not as the ultimate. And then with human operations down on the surface, there's going to be a lot of things that we're going to need to develop in addition. The mobility, the power systems, ecosystems for that. We're not really seeing out of those workshops that there was a lot of value to developing those on the lunar surface. So that's my controversial one, and thank you. I'll go on to the next chart. I wanted to touch on this one real briefly, and this gets back to Bob's talk yesterday too. This came out strongly in our workshops and in another workshop that I'm going to talk about just in a minute here. It's so important to tell the story. And I just love this picture. I stole it off the internet. I think it's for Udvar Hazy Center. But it really captures it. You know, we've got to inspire and capture the imagination of little guys like that and little girls like that. And it's telling me I'm done. So part of that is celebrate the successes. We're doing things now. We should be excited. I mean, I see Charlie get up here and get excited. I get excited. That was cool watching the booster firing yesterday. We're going to have a lot more of that kind of stuff. And the public, honestly, thinks NASA is gone. They think when we stop flying the shuttle, the space program's over. So every time I go to a party at my in-laws or something like that, I tell people that we're not dead. We're here. We're doing a lot of stuff. And we ought to all do that. We ought to talk to our neighbors. We ought to go to schools. When the space station goes over, get folks out and, you know, look it up on the website and tell folks up there that 6 people up there right now, and they're doing various things. Pick your favorite one and talk about it. That's all it takes, is get that word out there a little bit. And we got to use the media, and we got to use the entertainment industry. We've got some exciting things coming up this year. The Martian, the movie The Martian's coming out. I don't know if all of you have read the book The Martian. There could be some really neat tie-ins that we could use to get people more excited and interested, or just aware that we're still here. So that is a very important aspect, I think, of the whole sustainability, is to not be ashamed or shy about telling our story. This was a very interesting, I was really talking about the Affording Mars workshops, but just a couple of weeks ago, another group got together, and it was sort of the non-traditional folks, you know, that I think got this, that sort of instigated this and got it going. But a lot of folks from companies like mine and Boeing and Lockheed Martin also came, and we got together. And it was, again, that same kind of experience where I think I probably wouldn't be wrong to say a lot of us went in thinking, we're not going to have any common ground here. We're not going to be able to talk to those guys. And lo and behold, we had a lot of things that we did agree on. And you can read the statement here. I think a lot of you have seen this on the internet, but I just wanted to call your attention to this as well. I think we're coming together. We're beginning to agree on approaches. We're beginning to agree on ways we can do this for a lot lower cost. And it's going to push us through that barrier. Just like we pushed through the sound barrier, we're going to get through this 20-year barrier, and we're going to get to Mars. Thank you very much. Oh, and I forgot my last point. Coming back to Bob's talk yesterday, here's where you can be the hero. Some of you may say right now, well, I'm not sure I agree with those points Cassady just set up there. So in May, 5 through 7, be the hero. Come to Humans to Mars at George Washington University and express your opinion. Tell us why we're wrong. Let's get into that dialogue. I want you to join in with us as well. Thank you.
Given your scenario of a cargo mission followed by a human mission, you mentioned the sample return. And now, if you had that scenario, I guess the humans would be returning the sample. What would be the justification for having a separate sample return mission if that detracts from the justification of having humans go.
Okay, so the thinking was we're going to be needing to do, is it on? Can you hear me? The thinking was that we're going to be doing these precursor proving ground missions through the 2020s. There may be an advantage to doing an EDL demo in that same time frame to prepare for the human missions before we're actually ready with the hardware. That's going to be late 2020s to early 2030s when we're ready with that hardware. So the idea was, looking at the profile, the budgets and things, it might be a robotic mission that would be worth doing. And you'd combine it with a robotic sample return as well as potentially ISRU demo.
Let me comment on that as well, because we have to get out of the mindset of the Mars sample return. There is not just one and we're done. There are a lot of different goals of returning samples. First, robotic sample return does not negate the value of detailed in situ exploration by humans and return of a more carefully selected, wider distribution of samples. So it's not a sample return, it's got to be a sample return program. It's a scientific program. It's a scientific exploration program.
Let's talk about the boogeyman a little bit. So considering kind of the sophistication of parametric analyses that are being done at NASA right now with joint confidence level modeling, to what extent do you think that changes the calculus this time? You know, when we think about the space exploration initiative and the $400 billion figure that was put out that spooked Congress, to what level do you think JCL and EVM, cadre, all these various mechanisms ensure this time that it actually is funded?
So I think the approach, the overall architecture with the split mission and the cargo, has the, as somebody described, I think Steve Jerzyk again yesterday referred to being on the HEF team and having Kent Houston, I think it was, refer to the gear ratio. It does a tremendous amount. It drops that big figure of merit that everybody uses as initial mass in low Earth orbit. And it drops that way down. So from just a pure total dollar figure, that helps a lot. In terms of the approaches, one of the other things that we've been discussing a lot is risk posture. And things like, would you send the crew on the way out without the booster propellant, chemical propellant or other, that you need to get them back? Would you rely on that, be sent out on the slow boat and be waiting for them out there? Things like that could have a big impact too, and that's going to play in. It's going to be an overall approach that we have to take, where we are going to have to be a little more willing to take a risk posture that's not like where we are today.
This is a question for Joe, and I was wondering if in all of these recent workshop studies there has been a pathway emerge, or even a hint of a pathway, which would allow us to get humans to Mars in the 2030 period without a substantial increase to the NASA budget. I think the thing that keeps killing us, it isn't just the sticker shock, but the miracle has to happen, that the human element of the program has to double. And I think we all realize that simply is not going to happen in the current budget environment that we've got in the U.S., with increasing pressure on the budget for entitlements and so forth. So the specific question, I guess, would be is, do you see a pathway emerging that could be done for the more or less constant $8 billion a year that NASA has got for human?
Yeah, thanks, Greg. That's a good question. And I should have said that. I was trying to convey the other part of the approach that we're laying out. When we did the second workshop, it is very much live within your means type approach. We've had people at the workshops who were involved in the space station program, which also dealt with sort of the flat to very slowly increasing type budget scenario. And so the answer I give you is, We're not quite there yet, but what we are starting to do is we're starting to take those 6 elements and juggle the pieces around and figure out, you know, when certain things could fit in. And some of them, you know, I think the other thing people would be surprised about, some of them aren't as expensive as you might think. And part of that is we're going to leverage things that have been done in the commercial side. We're going to leverage the international partners. But yes, we are, the short answer is yes, we are taking the approach that we're not going to get a doubling of the human spaceflight budget. We're going to have to live within our means, and we're trying to figure out when we can develop all those elements we're going to need and plan that out. And right now it looks like we're pretty close to making 2030s, maybe not the early 2030s, but somewhere in the 2030s. I got the challenge yesterday from Norm Augustine that we got to do it before 2040 so we can do it before he's 104.
Okay, great. One other note, the performing arts
So a question I have is, how do we finance this if we don't have the budget from NASA or other government agencies? You know, out of the Apollo program, there was a long list of technologies that were ended up being exploited from NASA's developments. Many companies made money on those types of activities. Has anybody approached the commercialization of future Mars technology as a funding source? I mean, Apple sits on a few billion, as well as Microsoft and other companies. I mean, if you gave them exclusivity perhaps on some part of that technology that would come out of such a flight, would they be willing to cough up, you know, 100 million? And again, if you have 100 million here, 100 million there, it may get to $1 trillion at some point.
Yeah, it's a fair question, and I certainly think, and you saw on that chart out of the Pioneering Space Summit, one of the things that was part of that statement that came out of that is looking at the public-private partnerships as one of the means for doing this, as well as the international partnerships. So again, and I do want to reiterate, we're looking at this as needing an Apollo-style, you know, what people have referred to as the Washington Monument. If you look at the NASA budget, the big spike that was part of that budget in the 60s, that's not going to happen. We know that. We're looking at trying to do this incrementally within a budget that's not, you know, much more. I mean, the NRC made a really good recommendation. If we could get that, that would be wonderful. It would really improve the probabilities that the previous gentleman referred to of being ready in the 30s. But yeah, definitely we'll bring in the private side. The other thing I think you're seeing is as NASA goes further out, the private sector's coming right in behind. They're going to fill in the low Earth orbit commercialization. We've already got commercial cargo. We're going to get commercial crew. There's guys out there that want to mine asteroids for resources. So those kinds of things you're bringing up are not far-fetched at all.